How are y'all?
Good. Good. Yeah.
Good. Nice to see all of you today. So our first exam, 1 week from today, all of your homework and your chapter 6 and 7 quizzes due that day as well. Anyone have any homework questions? All right. Okay. So we finished this problem with force. Just a reminder, the difference between the force integral equation and the work equation that we're using is essentially right here with this function. With force, this is the width function. With work, it was the area function. So the area that our rectangles or our slices make give us the work. The width of our slices or our rectangles give us the force. So did anyone have any questions on this example 7? All right, we have two more examples from 6.7 to look at. And so we have a diving pool that's 4 meters deep, full of water, a viewing window on one of its vertical walls, set up an integral needed to find the force on the square window that's 1/2 meter on each side, with the lower edge of the window at the bottom of the pool. So to find the force, we're remembering this equation: density times gravity times the sum. We've got our integral. We have the width function, the height of the lift function h minus y, and dy. So we need to find w of y and h of y. Okay, so there's let's say that's our pool. It looks like window on a vertical wall. Here. So there's our viewing window, our dimensions. This is 4. So the width function then is just determined by where we're putting our cross sections. And since we want to determine rather, the force on the face of this viewing window, we're only going to fill that up with our rectangles. So our rectangles are through here. We've got to measure the width of the rectangle. So the width of our rectangles, 1/2. Does that make sense? We're not measuring the force on the entire face of the pool, just of the viewing window. So that's why our rectangles are that way. And then the h minus y function, what would that be?
4 minus y.
4 minus y? Do you all agree? That 4 minus y? Remember that height is the height of the container. So we want to, not the viewing window, but the entire pool. 4 minus y. Anybody have any questions on that? Okay, so we have density of water was 1,000, gravity 9.8. There's our function we're integrating. And our bounds are from where to where?
0 to 0.5.
0 to 1/2. What do y'all think? 0 to 1/2? So we're just determining where our cross sections are running. or our widths are running rather. So if you have that centered at the origin or whatever, this is 0 and this is 4. Okay, so we're filling this region up. So we do want to stop our bounds there at 1/2. Does that make sense? Okay. So 0, lower bound, 1/2 upper bound. Excuse me. All right, so that's the setup for that one. Anyone have any questions? Yep.
Why is gravity in this equation again, the force of gravity?
Sorry, say that?
Why is the force of gravity in this equation?
Why is it?
Yes.
Remember, force was mass times distance,
Yes.
right? Force, mass times distance. I lost my train of thought.
The force in this case caused by gravity.
Say that again?
The force in this case, so we're measuring the force a liquid is applying on something. The force is caused by gravity.
Yeah, I guess. I guess we can say any force is acted upon by gravity, so.
It's like the water pressure that's acting on the surface is caused by the weight of the water on top of it.
Yeah, like, I guess you could think of it that way.
Okay, so yeah, like the deeper in the water we are, the more pressure there is on the wall at that point.
Right.
Okay,
Right,
that makes sense.
yeah. All right. Okay, so then question 9 is a similar. So what would change in question 9? Let's think about that for a minute. Okay, so that's the kind of the situation here. So in our force integral, what changes?
Just the limits of integration.
Just the limits from
1 to 1.5.
1 to 1.5.
So,
What do y'all think? The height of the container didn't change, so that, distance to your cross section, or the height minus the distance to where your cross section is located, some y value didn't change. Also, the width of each cross section is still 1/2. But this time we're filling this from here to here. So again, if we're situating that at 0, it's 1 meter above, so this is already 1 meter above starting at 1. That limit of integration there is 1 plus 1/2, 1. That's all that's changed here. Make sense? Any questions? All right. Someone asked me a question for 6/7's homework. There was a hemispherical. That's just a summary. There's like this hemispherical thing and I forget if it was a work or force problem. But that was, you were given something like that and it said find the work or the force. So most of these we've just kind of set up at the origin, but it doesn't really matter how you situate these in the XY plane. What that's going to affect is the overall equation that sort of governs the shape of that tank. So for something like this, I think intuitively there's maybe two main ways we would look at that. We would say, well, maybe it's here where that's terrible, but maybe it's situated here with its center at the origin, or something like this where it's above the axis here, like that. I think those are probably the two most common kind of setups. But again, if you're looking at or questioning how to set something up or where to put something, maybe look at the scenarios and which one gives you the easier equation is the one that I would stick with. So this here would be an easier equation just because the governing equation would be that of a circle. We've centered it at 0, 0. So you don't get any of this kind of offset circle stuff when the circle's centered at the origin, right? So like in this situation, our center would be not at the origin. So it's a little bit more, I guess, a little bit more difficult of an equation to work with, but you can certainly work with that. But I think the more natural choice is the one centered at the origin. So again, center it wherever you want. It doesn't really matter. Naturally, the other thing that's affected are the bounds. If it's this whole thing we're talking about, the bounds are different. So you just got to pay attention to that, which is why it's really important to draw a diagram of some sort, so you're not referencing two different situations. Are there any other questions on 6, 7? Okay, 7.3 is kind of the oddball. It's from chapter 7. That's why your quiz says quiz chapter 6 and 7. You do have one section from chapter 7. And here we're looking at hyperbolic trig functions. Primarily, this is a pretty short section, all things considered. There are applications to hyperbolic trig functions. It's like a whole new door we're opening, but we're not going to do a whole lot with these. We're going to look at the functions, kind of where they come from, and primarily focus on their derivatives and their antiderivatives. So we're going to start off with defining both the hyperbolic sine function and the hyperbolic cosine function, and then we'll see, kind of trying to make a connection to where they come from. But this is hyperbolic sine, hyperbolic cosine. Sometimes this is just pronounced sinh, and hyperbolic cosine is pronounced cosh. But you can call them hyperbolic sine and cosine if you want. I don't know how to sinh and cosh. I don't know how to write that out. But we see that they are actually exponential functions. So the definition of both of those are there. Very similar definition. Sine's got a minus, cosine's got a plus on top. And the graphs are as follows. Okay. So we'll just kind of briefly state where they come from on the next page. When we can find the derivatives of these things, because we know the derivatives of exponential functions, and that's how they're defined. So we'll show where the derivative comes from, but just like in calc, when you show where a derivative comes from, the derivative of sine is cosine, even though there was like a proof involved with that. We always just say the derivative of sine is cosine. It's the same thing here. We're just going to show where the derivative comes from, and then use that fact. So it's taking the derivative of sinh, we're going to take the derivative of e to the x minus e to the negative x over 2. So we're really just taking the derivative of e to the x minus e to the negative x all over 2. The derivative of e to the x is e to the x. Derivative of e to the negative x is negative e to the negative x. And it's still all over 2. And we recognize e to the x plus e to the negative x over 2 as the hyperbolic cosine. So the derivative of hyperbolic sine is the hyperbolic cosine. There are some parallels with the circular trig functions, but there are some differences too. And so with that in mind, we can see that this is going to give us kind of a similar result. So derivative gives us now e to the x minus e to the negative x all over 2, which of course is hyperbolic sine. I'll make sure to point out which things you should know for the exam once we get there. All right, so hopefully that's pretty straightforward. Anyone have any questions on this initially? Okay. So we'll come back to that in a moment. There are some parallels we can make, although we don't really work with them. It might be, a little bit more descriptive as to where these things come from. So when you take a point on the unit circle and you describe it by x and y, we also could describe that by, well, let's do this. We also described each point on the unit circle, x and y, in terms of sine and cosine, right? So unit circle equation, x squared plus y squared equals to 1. And we said that vertical distance was the sine, was r, but our radius is 1. So we're kind of, the radius is in the mix, but it's always 1 here. So we could also equivalently in this situation describe a point as cosine sine. So we have this length. We also have this arc length here. So does anyone remember what the length of this arc is? How you find it?
You multiply the degrees and radians by the radius.
Yeah, so we can call that S, I guess. The length of that arc was the radius times theta. Just here is just theta. So oftentimes, since we can characterize this length here by theta itself, let's call this t. For whatever reason, if you look at other references for this, t and theta are the same thing, just based off of that relationship there. So sometimes, if we're describing it that way, we might have saw this point xy described as cosine of t and sine of t. And when we look at the area, when we look at the area of that sector, anybody remember the formula for that? So the area was 1/2 r squared theta. Or we could say that's 1/2 t, because theta and t are the same thing. And so the notion of this area here, we can say it's 1/2 t, or we can say that t is twice that area of the sector. So we sort of have a similar characterization when we look at the hyperbolic trig functions, although again, it doesn't really come into play for what we're doing. It's just when we can remember some of this stuff from circular trig functions, and then we look at the hyperbolic trig functions, we do see sort of this analog going back and forth. So those are some of the key aspects of our circular trig functions. The hyperbolic trig functions have come from the unit hyperbola. So the unit hyperbola, we've got, I guess it's opening, if you will, in the x direction. So the equation for this hyperbola would be what? Anybody want to take a shot at that?
Did you say the formula?
Yeah.
It's fractions.
Fractions. Yeah. So it's x squared minus y squared equals to 1. So just pausing there for a moment, when we go back up to the circular trig stuff, remember I guess the fundamental identity for the circular trig functions was cosine squared plus sine squared equals to 1. That came from the fact that x was cosine of theta was treated as x, so we have cosine squared plus sine squared equals to 1. The Pythagorean identity, if you will, here, it's not really Pythagorean, but the identities are different because this is going to be cosine, y is going to be sine, cosine squared minus sine squared equals to 1 for the situation when we're on the unit hyperbola. So what we do is we take some point on the hyperbola. Again, we're going to call that x and y. I mean, it's not like I don't think it's like a one-to-one correspondence to the situation where we're talking about a circular trig function. But we're going to call this point xy. It can be described as the hyperbolic cosine of t and the hyperbolic sine of t. So that role of theta we saw in the unit circle was replaced by t just because that arc length and the angle measure were the same. Here, what t represents, so it's not as straightforward as an angle. We say we look at the point on the unit hyperbola to the origin, and the area that's kind of similar to the area we were looking at the circle is this area here. So if we look at this area, it's kind of the same because the area is this parameter t divided by 2, or like we had over here, 2a is equal to t. So that's kind of how we think of t here. It's not as, I don't know, it's not as intuitive, I think, as it was with the unit circle. But it's kind of a similar idea, like these points on the unit hyperbola can be described by these hyperbolic trig functions. Just like the circular trig functions describe points on the unit circle. So that's kind of the parallel.
Is it the ellipses that are fractions?
Yeah. Well, hyperbolas too.
Oh.
So like, you know, we have, I mean, you can have this. This was a equation of a hyperbola centered at the origin. Yeah, and then the ellipse was this. And all the A and B tell us, sort of gives us an idea of how like wide or narrow the parabola is, and in what direction does it open? Like, does it open this way or does it open this way? Okay. All right, so that's kind of the parallel. There's a lot more to this stuff, but we don't really get into any of that. So some of the identities have changed because the equation governing a hyperbola has changed from plus to minus. So as you can see here, here are a few of those identities. So I guess the fundamental one or the main one is this one here, just coming directly from the equation of the hyperbola. And then from that one, just by dividing by hyperbolic cosine or hyperbolic sine, we get these other two down here. They're not quite what they were with circular trig functions. And then we have these definitions of hyperbolic sine and cosine. So those things that we've boxed, you should know for the exam. The other identities aren't necessary. You only need those. We have this kind of similar relationship between the reciprocal functions that we did with circular trig functions. So, you know, you can just remember that. You don't necessarily, I won't ask you, you know, what the exponential definition of these ones that we didn't box are, but for sure for sine and hyperbolic sine and hyperbolic cosine, you should know those. Okay. This is just a graph of the hyperbolic tangent function. It rhymes with Blanche, so they say tanh or hyperbolic tangent. Defined as hyperbolic sine over hyperbolic cosine, and when you do that, when you actually do that work, you end up with this here. Okay. So like example 3 says find the hyperbolic sine plus the hyperbolic cosine. You just want to use the definitions, the exponential definitions of each. To find out what that is. So there may not be like a hyperbolic trig representation for some of these things. We already have a common denominator, and we have 2e to the x over 2. Which is just e to the x. You know, they have a fancy name because they come from the unit hyperbola. At the end of the day, they're really exponentials. They're all exponential functions. As far as the derivatives go, I think they're on the. As far as the derivatives in the integrals go, there's only a few of these that you should remember for the exam. And those would be derivative for hyperbolic sine, cosine, and tangent. And the same thing with the antiderivatives. Antiderivatives for hyperbolic sine, cosine, and secant squared. Those you should know for the exam as well. So like another parallel is, if we have to provide or prove that the derivative of hyperbolic tangent is hyperbolic secant squared, there's a few routes we could take. We could say, well, what was the exponential definition for tangent, hyperbolic tangent? And then try to compare that to the definition for hyperbolic secant squared, but we don't have that. We could use the definition of the derivative, which would be really difficult, proving that the limit as h goes to 0. Another thing we could do is we could say, well, I know that hyperbolic tangent is the same thing as hyperbolic sine over hyperbolic cosine, and just find the derivative of that. So what do we got to use there? Quotient rule. All right, so the quotient rule said the derivative of a quotient was what?
The first times the derivative of the second times this times the derivative of the first all over the bottom squared.
The bottom squared, yeah. So what's the first and what's the second? What are you thinking of? The top and bottom, you mean?
No, the e to the x minus e.
Okay, yeah, so we could say that so let me write it out. You're thinking this here? Like that? So write them like that, and then take the derivative of that? No. I mean, you could, right? It's not, the 2's cancel out, and you just have e to the x minus e to the negative x over e to the x plus e to the negative x. But if you were looking at that, right, you still have a quotient rule involved with this as well.
So yeah, it would be the top times the derivative of the bottom times the derivative of the top.
Yeah. So I mean, we could do that with the exponential as well. But we don't have an idea of what the exponential representation of hyperbolic secant squared looks like. Other than that, it would be fine to do. We're going to do the bottom times the derivative of the top. What's the derivative of hyperbolic sine? Again, this thing, hyperbolic cosine. So there's the bottom times the derivative of the top minus the top function times the derivative of the bottom. Derivative of hyperbolic cosine, hyperbolic sine. Bottom derivative of the top times minus top derivative of the bottom. We just put all of this over the bottom function squared. So really, with the regular trig functions, circular trig functions, you basically needed to show the derivative for sine and cosine, and then you just use other derivative rules to find the derivative of tangent, secant, cosecant. Right? That's kind of what we're doing here. So we have cos squared minus sinh squared all over cos squared. Squared, and then where from here? Where do we go from there?
The cos minus the sine to -1.
Right. So cos squared minus sinh squared is just 1 over cos squared. So reciprocal. Yeah. Derivative of the hyperbolic tangent is hyperbolic secant squared. Any questions on that?
I went a different way.
What'd you do?
I just took cosh squared x minus sine squared x all over cosh squared and split it into two fractions.
Yeah.
Is that still cool? Using
Sure,
just a
yeah.
different identity?
Yeah, totally valid.
Okay.
Yeah. So you just divided these,
Yeah, so it was like 1 minus tangent squared.
Yeah.
Which is,
and then you divided these.
yeah.
Yeah. So you have, yeah, 1 minus hyperbolic tangent squared, and then we can use one of those identities. 1 minus the hyperbolic tangent is hyperbolic secant squared. All right, a few derivatives. Well, I guess one derivative, a couple of integrals. That's really all we have for 7.3. Okay, so we've got to find the derivative of hyperbolic sine of square root of x squared plus 1. So the chain rule has to be involved here. So you take the derivative of the outside function, which is this, derivative of the outer, leaving the inner function alone. So we're leaving that alone. Multiplied by the derivative of the inner function. So I'm going to do this over here. Derivative of, we have x squared plus 1 to the 1/2. So you've got another second chain rule, I guess, if you will. Derivative of the outer function. Leaving the inside function alone. Times the derivative of the inner. Okay. So we've got this times 2x so that's all here for this piece. We have x times x plus 1 to the negative 1/2 times our original function, our original piece here. I guess 3 chain rule. Okay. Any questions? That's about it. Unless we want to write this with positive. Unless you want to write that with positive exponents. I don't really care how you write those kinds of things. There are some things that we do. You can see that we've used the derivative a few times through chapter 6 already. There's a couple of instances in chapter 8 when we integrate, where we use the derivative again. And when we talk about sequences in series, sometimes we use the derivative to test if something is decreasing. So the derivative is not anything that goes away. Even in some of these intermediate things we do, the derivative is there. So hopefully you remember the derivative rules. If not, you got to catch back up somehow. Okay, how about the antiderivative for the hyperbolic cosecant?
Would it just be 1 plus sinh squared?
Yeah, you could write hyperbolic cosecant as 1 plus.
Oh, it's cosecant.
Yeah.
Or it was the
Oh,
Just writing it wrong.
okay, yeah, okay, sorry. Yeah, not cosh.
What's that?
Cosec. So sometimes you can just think of the regular trig functions. What if you were asked to integrate the hyperbolic cosecant squared? I screwed all that up. Hyperbolic cosecant versus cosecant squared.
So you just make that one to the 1 over, let's see, square.
Well, yeah. I mean, you could certainly do that. You could write this as this.
So we can just make that one to,
But then, yeah, how do you integrate a quotient? The integral doesn't. What's the word? Distribute, I guess, across the top and the bottom. It's not that straightforward. So I mean, you can't write it out like this, but then it doesn't really help you as far as like integrating it.
so I mean, we can like explanation is that the sin square, like the 1, I think it's the 1 minus the sin choose x minus 2.
Which one? So what? You mean you're thinking of one of these identities here?
About like the sin 2.
Yeah. This one.
The
Because I don't know that they would help us. You still have that on the bottom. Because it's still 1 over that. Do we see that here?
I don't really see the answer, but.
What if you do,
So really,
because I remember when you did like sine squared, you did negative cosine over 2 or something like that?
yeah, 1/2 times 1 minus cosine of 2x. But it would be like the 1. Yeah, so we don't have one for that one. I mean, we have that 1 over sine squared, or 1 over hyperbolic sine squared. We don't even need to get that crazy with it, right? Remember, the derivatives are based on the derivatives. The derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. So the antiderivative of negative hyperbolic cosecant squared is cotangent. In other words, that. To move the negative around. I mean, I don't know. That's kind of why I put this one here. I guess maybe you didn't remember that one either. But the antiderivative of cosecant squared is negative cotangent. Let's see. All right, got one more here. So I'll take like 10 minutes and work this problem, number 7.
Yeah, these equations are.
So at this point, y'all, for us, whenever you see a product, we're gonna, once we get to chapter 8, we'll talk about how you take, in general, the antiderivative of a product, but it involves another technique. For now, when you see a product, 99% of the time, it's gonna be a U substitution. So the U substitution is here because that function, x squared plus 4, its derivative, missing a constant, but its derivative is also present in the integrand. So we have U substitution is undoing a chain rule. So that's kind of like a chain rule, right? If I told you to take the derivative of that, you would say it's whatever. You would say that it's this, and then apply the chain rule and say that it's times 2x. So, it's kind of the same idea. Working in reverse to find the antiderivative of something like that, reversing a chain rule or a product of two functions of x is a U substitution. Okay, so we have that. And, what you can do is say, well, there's not a 2 present in this original integral, but if I were to want this to, and this is essentially what you do anyways, but this is just a different way to think of it. There's not 2 times x times dx present. So you can say, well, if that were there, then I would have this very straightforward substitution. I wouldn't have to solve for my, my x, my dx. But all you're doing is, wishful thinking, multiplying your integrand by 2. You can do that as long as you divide the integrand by 2 as well, right? So that's essentially what you're doing when you solve this equation here to match up what you have in the original integrand. Okay, so we still have this 1/2 out here times the integral. Whatever. This 2x dx, 2x dx is now this du. All of that stuff's our du, but we still have the sine of u here. So sine of u, hyperbolic sine of u, rather. So that's all you have to integrate there. So antiderivative is hyperbolic cosine of u plus c. And then, you always want to resubstitute in terms of the original variable that was given to you. So don't leave it as this right here. Resubstitute for u, which was x squared plus 4. And that's it. If you're unsure, just take the derivative. The derivative should be the function, the integrand, that was present with the antiderivative. Okay, does anybody have any questions? There is one more. I didn't write it out. There's one more example. It's similar to something you did, something you'll have in your homework. So we'll take a break first and then look at one more example in 7.3. There's really not much else to cover. So the last problem from 7.3 I want to look at is and honestly my tires on my car are pretty crappy and it's snowing a lot, so I hope we can get out a little early. It's okay with y'all. Don't tell anybody. So let's look at the definite integral from 0 to natural log of 17. And we want to find the integral of hyperbolic tangent with respect to x. I know that this isn't mentioned in your section. We actually do like look at the antiderivatives of the other 4 trig functions in the next unit. And it's kind of based on the idea of the, or the strategy and how we're going to find the antiderivative of hyperbolic tangent. So I'll tell you that it doesn't involve any identities. I mean, like complicated ones. So the way we look at this, and you'll see it's the same when we look at the integral for tangent, the integral for secant, the integral for cotangent, and the integral for cosecant. They all follow a similar pattern. And so what you want to do here is you want to first write this as hyperbolic sine over cosine. And the thing to remember is this derivative of the natural log of a function. What would the derivative of the natural log of a function be?
1 over the function.
1 over the function? Do you all agree? Times the derivative of the function, right? Don't forget the chain rule. All right, so if that's the case, then this is the case. The antiderivative of f prime over f is what? Right, the natural log of that function. Remember just the caveat here that we use the absolute value when we go backwards, plus c. That's typically so we can match the domains. Here we would just exclude when f of x is 0. We could have when f of x is negative. So that, you know, over here in this world, this scenario here, these things could be negative, and that's why we put the absolute value there, just so we can reconcile more of their domains. So that's a really key like integral to know, because if you don't remember it, it's fine, because these things are just calculated, like if I have f prime over f, they're just calculated by a u substitution, and the u substitution gets you to 1 over u, which gets you to ln of the absolute value of u, which gets you where you need to go, but it's less efficient. That's I think an important pattern, if you will, to recognize. So when we rewrite this hyperbolic tangent as hyperbolic sine over hyperbolic cosine, then what we're looking at is exactly what we have over here in red, right? You have a function on bottom. The derivative of the hyperbolic cosine is the hyperbolic sine. So here's the exact scenario that's here. There's your f of x, excuse me, and there's f prime of x. So if you know, again, if you recognize that pattern, then you can immediately jump into the antiderivative of this is just the natural log of the absolute value. Sorry, is just the natural log of the absolute value of the hyperbolic cosine. You know, and again, if you don't, that's fine. But this is a u substitution because we have a function and its derivative sitting here. And then this instance, then your integral is then, you know, find your du, of course, but then your integral is just 1 over u du, which leads you here. Okay. Does that make sense? Does anyone have any questions or comments there? Okay, so that's f prime over f. The antiderivative of f prime over f is the natural log of the absolute value of the function on bottom. So that's what we have, and we're evaluating that from 0 to 17. Sorry, 0 to natural log of 17. Go ahead. All right, and so they want an exact answer. So I guess, of course, you could put that into your calculator, but we could also remember the exponential definition for the hyperbolic cosine. And the thing to note about the hyperbolic cosine, if you haven't already, is the hyperbolic cosine for any argument x is always positive. Exponential positive, this exponential is positive, we're adding it and dividing by 2, positive numbers all the way around. So that's hyperbolic cosine is greater than 0 for all x. Which means we don't need the absolute value around the hyperbolic cosine anymore, once we know that, right? The absolute values were there just to ensure that whatever we're taking the natural log of was indeed positive. But hyperbolic cosine is always positive. Is hyperbolic cosine ever 0? No, never 0. So you don't have things to worry about when we're taking the natural log of this quantity. So I mean, that's our next step, I guess. Get rid of the absolute value. If you want to leave it in, fine, leave it in. It doesn't really matter. So we're just going to rewrite hyperbolic cosine like that because our bounds, particularly the upper bound, is a bit weird. So it involves a natural log. With e's in there, we can get an exact answer. Okay. So, yeah, that's about all I wanted to say there. From here, should be pretty straightforward, hopefully. Does anyone have questions on that example at all? So when you look at, to parallel this, when we look at the antiderivative of the regular tangent function, the same idea is there. It's sine over cosine, but it's not quite in the form function and derivative, right? Because we know the derivative of cosine is actually negative sine. We don't have a negative sine. So it's just like that. If you go through all that u substitution stuff, you get the same result. But so we say, well, the derivative of cosine is negative sine. It would be awesome if this were negative sine, right? If that were a negative sine, that's what we want. Well, I multiply this by -1, I multiply all of this by -1, and there I have a perfect f prime over f relationship there. So then we would say that the antiderivative of tangent is the negative, and this negative here, natural log cosine. So really, I mean, you could have talked about that in Calc 1 because it is just a u substitution, or it's in logarithmic form, if you will. But anyways, we will talk about those next unit. Everybody good with this then? All right, that's really all I have for 7.3. So this is the content for exam 1. I'll just circle the number of questions for that concept. So you're going to have one question with displacement. And distance traveled. You should be able to identify. I'll post this under exam review. So this is what's going under exam review. I don't have an actual review. So identify when the object's moving up, down, or left, right. In other words, when motion is in the positive or negative direction. So you had a few of these in your homework too. So one question regarding that. And so for something like that, you should, kind of like the ones we did in class, graph it. That way when it comes to computing the distance traveled, you will know which regions are positive and which regions are negative and how to split that up appropriately. There's going to be six questions over the disc or washer method. And the shell method. This was, of course, from 6.1. This is 6.3 and 6.4. And for these 6 problems, the graphs will be provided. There's going to be one question for arc length. One question over surface area. One question where you're given a density, which was rho of x. So you're given that, you want to be able to find the mass. One question with work on a spring, or with, or on or with a spring. Then this, we're going to assume that these springs obey Hooke's law, which gives us the force function spring constant times x. I'll look at these sections in here too. Surface area, that was 6.6, arc length was 6.5. The next few will be from 6.7. Work on a spring, there's going to be one work problem that involves lifting or pumping water. One question for that one. one question for force. So force on a, I guess, I don't know, dam face or trough face, whatever. One of those. Maybe also one question for derivatives of hyperbolic trig functions. Like I said, you should know the things that we boxed in red on Chapter 7's notes. And then there'll be two questions for antiderivatives with hyperbolic trig functions. Of course, that's 7.3. These are from 6-7, all of these. So that's the makeup of the exam, just so you can have an idea of what I'm looking for, what I'm testing over. Hopefully that's somewhat helpful. But does anyone have any initial questions on that? I'll post this to G2L.